Today we're talking about conditional probability, and this is a way of updating or changing a probability that we assign to some event if we have some extra information. So, for example, let's take the situation where I flip two coins. And the question is, what is the probability that both coins are heads? So in this case, event B would be the event where both coins are heads. Well, that should just be 25%. It's 1/2 times 1/2. But if I happen to reveal, hey, this coin was heads, that's going to change the whole probability. Now, what's the probability that both coins are heads? Well, this is 1, this one is heads, and this one is 1/2. So the total probability should now be 1/2. So what we're talking about is the probability that they're both heads given some new information. Cool. All right, so notationally, we're going to use this format, which says that the probability of the event B given A is whatever it is. So this thing, this vertical line, we can just read as given. This is where we're saying that this is a conditional probability. We're not just talking about the probability of A, it's the probability of A in a certain circumstance. Well, sometimes we can just ask that directly, like we did with our coin flips. But more generally, we can say that the probability of B given A is the probability that both things occur, so A and B occur, divided by the probability that A occurs. Let's do another example. Here, the situation is that I am drawing a card at random. So I've got a standard deck of playing cards, and I draw a card at random, and let's say that A is going to be the event that the card that I draw is an ace. B is the situation where the card is red. So I can ask questions, so I've actually asked these in the last video. I can ask questions like, what's the probability that the card is an ace? Well, there are 4 aces out of 52 cards, or 1/13. We could also ask the probability that the card is red. Well, there are 26 red cards out of 52, or put another way, half of the cards are red, so the probability of B is 1/2. Okay. I want to break this up a little bit more. All right, I want to use this Venn diagram to represent what's going on. So this circle A should represent all of the situations where the card is an ace, whereas the whole circle B is the situations where the card is red, and then the overlap is going to be the situation where the card is a red ace. And there's a couple ways we can go about filling this in, but let's just say that working with 50 seconds, there are 2 ways that the card is both red and an ace. And then since there are a total of 4 ways that the card is an ace, there are 4 aces, the total number here should be 4 50 seconds, which means that the number that goes in this slot is, not 4, is 2 50 seconds. By similar logic, if 26 cards are red and 2 of them are already accounted for, then we need another 24 remaining. And then lastly, 2 plus 2 is 8, 28. We should have, I believe, 24 50 seconds on the outside of this. All right, so when we ask something like, what is the probability that the card is an ace, we're asking for cumulatively all of these probabilities. If instead I'm asking for a conditional probability, like the probability of B given A. So what we mean by that is assuming that the card is an ace. So our world of possibilities has narrowed down to only the situations where the card is an ace. So if we're in this situation, now what's the probability that the card is red? So on one hand, there are two ways that it's not red, and there are two ways that it is red. So the probability that it's red ends up being a 50-50, and this thing, probability of B given A, ends up being 1/2. So sometimes we can sort of logic our way through a question like this, but more generally, we have sort of a formula which is putting down in terms of an equation the logic that we just sort of said. So the probability of B given A is going to be the probability of A and B divided by the total probability of A. Well, this is the probability of A and B is just this middle overlap probability. That's going to be 2 50-seconds. And the total probability of A, well, yes, we've already calculated that. But let's say that we just had our Venn diagram here. We want to add up all of the terms in A. So there's a 2 50-seconds here and 2 50-seconds here. Cumulatively, that is 4 50-seconds. And then if we do some math, we should see that same answer. All right, in this example, you might point out that our probability hasn't changed. The probability of B given A is 1/2, and the probability of B is 1/2. Assuming A hasn't changed the outcome, hasn't changed the probability that the card is red. This is in contrast to our first example, where the probability that they're both heads, this B event, started off as a 4th, and then when we got some new information, we updated the probability to 1/2. So this second situation, where the probability doesn't change, is an indication, or actually this is our definition for what it means for two events to be independent of each other. This is how we'll define our idea of independence. So two events A and B are independent if the probability of one of them doesn't change if we assume that the second one happens or not. So the presence of A, or the assumption of A, shouldn't change the the probability that B happens. The probability that a random card is red is 50-50. The probability that the card is red, assuming that it's an ace, is still 50-50. So because that probability doesn't change, we say that the event A, where the card is an ace, and the event B, where the card is red, are independent events. So in the future, I'll probably occasionally ask, are these two events independent? And it's really tempting to say, like, oh, I don't think that they're interacting with each other. But if we have access to the probabilities, what we're really asking for is, does the probability update with this new information? So this, again, is not talking about any sort of causality between them. That's not at all what the discussion is about. The question is just, does the probability change if we have any new information? I also want to mention another idea that can often be confused with this notion of independence, and that is that two events A and B are disjoint if they can't possibly both happen at the same time. Here's an example of this. We could choose a date at random, and then we could say that event A is the probability that that day is a Monday, and B would be the probability that that day is a Wednesday. So what's the probability that A and B happen? The probability that the day is both a Monday and a Wednesday? Well, that's 0. And that happens because these two events are disjoint. So if we wanted to draw a Venn diagram, we typically would draw it where the circles don't overlap at all. So I would say that this is a diagram where A and B are disjoint. So again, to contrast this with this notion of independence, if we have a Venn diagram where we have A and B, two events are independent if the probability of one of them occurring, so let's say the probability of A, in the entire frame is the same proportion as the probability of A given that we're somewhere in B. So in other words, that this proportion, this part over the whole part, the whole B, is the same fraction as this part over the entire possibility, over 1. Anyway, main distinction, disjoint means that they can't possibly both happen. Independent means one of them happening doesn't affect our probabilities of the other one occurring. So this equation that I've now mentioned a couple times actually lends itself to some rearranging. So this actually gives us the generalized multiplication rule. So remember, I had previously said that the probability of two events occurring, P and B, we're just going to multiply P of A times P of B. And there was an assumption there was a condition, and that was that A and B are independent. Well, now we've defined independent, and we can actually generalize this a little bit. We can say, oh, this is the probability of B given A. So the probability of A times the probability of B, so if we multiplied this term over, the probability of A times the probability of B given A should be the probability of A and B. So this is the generalized multiplication rule. And it's worth pointing out that if A and B are independent, then the probability of B given A should be the same thing as the probability of B. So if A and B are independent, then this simplifies to the previous multiplication rule we had mentioned before, which said that the probability of A and B is the probability of A times the probability of B, and this happens because this term equals this term. If they're independent, updating our B probability with A shouldn't affect anything. If they're not independent, then this will account for this generalization. So this rule is the one that we particularly care about. We mentioned the other one earlier because we were sort of just getting used to probability. This is the rule that we will almost always use. Just about any time in this class, it's going to be useful to draw a picture. And this is especially true for probability questions. Sometimes a Venn diagram can be really useful, but when dealing with conditional probability, tree diagrams are often the way to go. So here's sort of a generic version of a tree diagram. In the first stage, one of three things can happen, A1, A2, or A3, and so we're representing that with a three-way fork. After A1 has happened, either B can happen or it doesn't happen. Similarly, for each of A2 and A3, we are then faced with this next choice. It's worth pointing out that the order of these is a somewhat arbitrary choice. Depending on which information we have, we may want to first have the first fork in this tree diagram be dependent on B, and then deal with A splitting into A1, A2, and A3. Just bear in mind that it can go either way. Okay, so when working with this, it's usually helpful to label the edges with the probability of taking that fork. So if we're here, the probability of going in this direction should just be the probability of A1. Similarly, we could label this bottom branch with the probability of A3, etc. Once we get to the second stage, however, we don't want to just label this edge with the probability of B, because we're not just asking the probability of B, we're asking the probability of B given that we're here. So assuming that A1 has happened, assuming that we are at this point in the tree, then what is the probability that we go towards B? And so what this is asking for is the probability of B given A1. So one nice thing about writing these out this way is that if we want to know the probability of both of these happening, the probability of A and B, A1 and B, well, we can find that by just multiplying through. So we can multiply this term by this term, and that should be the probability of A1 times the probability of B given A1, which is the equation that we've been talking about.